Okay, so we're going to start in 4.1, which is on page 174, 175 in your book. We're looking at polynomial functions. Okay, so all a polynomial function is you're going to have something where we've got f of x equals, okay, here are the rules. It can have as many terms as you want, but you cannot have a variable in the denominator. If there's a variable in the denominator, it's not a polynomial. Okay? Your variables cannot be under a square root. If they are, it's not a polynomial. And similar to that, your variable cannot be raised to a fraction power. That's the same thing as some kind of radical. Okay, so those two are tied together. All right, but I'd like to explain it both ways. So, basically I'm telling you there's no way I'm dividing by 0, and there's no way I'm taking the square root of a negative, because those cannot exist to be a polynomial. So your domain of every polynomial function is all real numbers, because these are not going to be problems, right? Those are the only two ways we get a problem. So some examples of polynomial functions, you could have something like g of x equals 3x to the third minus 8x to the second plus 1. That would be a polynomial function. Something like this, h of x equals 3x to the 17th. That's a polynomial function, even though it's just one term. Okay? Or even something like this. If I had g of x was equal to 3. It's just a constant number, but that's also considered a polynomial function because it does not exhibit any of these problems. All right? So there's a wide range of polynomial functions. The next thing we're going to do is look at a few of them and determine if they are or are not polynomials. Okay, so here at the bottom of 174, example 1, it asks me to determine which of these are polynomial functions. For the ones that are, state their degree. Okay, so what's the degree of a polynomial? It's just the highest powered exponent. So if you look back on those last examples, like on the one that was, I don't know, what was it, 2x to the 17th I wrote?
Yeah, 3x.
3x to the 17th. The degree would be 17 there because that's the highest power. The one before that would be a degree 3 polynomial because it had a third degree, right, was its highest power. So that's all you got to do to state the degrees. So look at example A. Does it have any of the problems that I said before? Is there a fraction in an exponent? Is there a square root? Is there a fraction in general? No, there's none of those things. So that means A is a polynomial. Yes, it is. And what's its degree? 4. Absolutely. B, is it a polynomial? No, it's not, because there's a square root of a variable. Very good. C, is that a polynomial? It is not. Okay? Because I've got a fraction. I could divide by 0. Those are the things that we just got done dealing with. Those are rational functions. Okay? They are not polynomials. Looking at D. D is a polynomial. Yes. And what is its degree? 0. Right? I have no x to any power, so it's a 0 degree polynomial. E. Yes, it is. What's its degree? It's also 0. Very good. And F, is that a polynomial? Okay, this one looks a little different. Okay? So comparing, for instance, A and F, they're in two different forms. Kind of like what we've been doing with the rational functions. This one is already distributed out, right? This would be the general form of a polynomial. This would be called the factored form of a polynomial. So it is also a polynomial, yes. But now when I ask what degree is it, I need to distribute to get in general form before I answer that question. Okay, so I'm going to move this up to give me some room to work that out. So I've got negative 2x to the third times x minus 1 squared. Okay, so what does that mean if I've got x minus 1 squared? That means I have got an x minus 1 times an x minus 1. We distribute out. So that's going to give me negative 2x to the third times x, x squared. X times negative 1, negative x. Negative 1 times x, negative x. So negative x and negative x is negative 2x. Pretty good with all the, I'm combining steps together. And then negative 1 times negative 1 is positive 1. And now we're going to distribute one more time. Okay, right here. All right, this one's an easier one because the term on the outside is a monomial. Negative 2x to the third times x to the second is negative 2x to the fifth. Negative 2x to the third times negative 2x is positive 4x to the fourth. And then negative 2x to the third times 1 is negative 2x to the third. So this would be the general form, and that we started with would be the factored form. So now that I've got it in general form, what's its degree? 5. Very good. So the answer to F would be yes, it is, and it's a 5th degree polynomial. Okay, here's the next example we're looking at. I am charged with finding a polynomial that is of degree 3 who has zeros at negative 3, 2, and 5. Okay, so everything else is words that we've talked about up to this point besides the word zeros. Well, what does it mean when it asks me to find the zeros? Do y'all remember? No. Okay. This is what it means. All these words are used interchangeably. If someone ever asks you to find the zeros of a polynomial, that's the same thing as finding the roots of a polynomial. If they ask me to find the roots of the polynomial, that's the same thing as finding the x-intercepts of the polynomial. Those three words are used interchangeably. So since it tells me its zeros are at negative 3, 2, and 5, I normally think about that as being the x-intercepts. The x-intercepts are at negative 3, at 2, and at 5. So now, how do we normally find... Okay, well, let me think about this for a second. So I'm looking for f of x is equal to some function where I'm going to have x's raised to some powers, right? I don't know what they are, but I'm going to have some powers and some numbers and all that good-looking stuff here. How would I figure out where the x-intercepts were of this good-looking function? I would plug in 0 for y. And so I'll get 0 equals some good-looking function. And now what would we do from here? We would want this to be in factored form. Because if I could say this times this times this equals 0, then we set each one of those factors equal to 0, right? So if we think about it, I want my answers to be whatever all this jazz is over here. I want to end up getting x equals negative 3, x equals 2, and x equals 5. That's what I'm wanting to get, right? So those are called the roots, or those are called the x-intercepts, the zeros. What we're going to do is we're going to write them into their factors. So think about it. How do we get this? We set each one of these parentheses equal to 0. So now I'm going to take what I want to be the roots and set them equal to 0. So if I move the negative 3 over, this says x plus 3 equals 0. If I move this over, it says x minus 2 equals 0. If I move this over, it says x minus 5 equals 0. And so what is that telling me? Well, if these were my things in parentheses, they would give me the roots that I want. So I'm going to take these factors and plug them in to those parentheses. Are you following? That's kind of sloppy, but I kind of like that visual look at it there. So my function is going to be x plus 3 times x minus 2 times x minus 5. All right, and that's my answer in factored form. That will be fine. However, the only problem I have is I need to make sure that this is a third degree polynomial. So how can I tell what the degree is the way it's currently written? You could distribute those parentheses out to find out what the degree is. And that's probably what most people will do. Or there is a quicker way, but I mean, you have to make sure you're able to see it. This is an x to the first power, and what's it raised to? The first power. This is an x to the first power raised to the first power. X to the first raised to the first. So I've got an x to the first, an x to the first, and an x to the first. When I distribute that out, it's going to get me an x to the third. That's going to be the biggest one, okay? So I already know this is going to be third degree before I ever distribute it. But let's distribute it just to be careful, just to be sure that it's going to work out. Because just like we did with the rational functions, you're going to need both forms. So this will be good practice to go ahead and practice distributing. Okay, x times x is x squared. X times negative 2 is negative 2x. 3 times x is positive 3x. So I've got negative 2x, positive 3x. Those combine to give me positive x. 3 times negative 2 is negative 6. And I'm left with x minus 5. And now I have to distribute one more time. X squared times x is x to the third. X squared times negative 5 is negative 5x squared. X times x is x squared. X times negative 5, negative 5x. Negative 6 times x, negative 6x. Negative 6 times negative 5, positive 30. Give you a second to get caught up there. Everybody to here? Everybody's good? Now, like terms. Do I have anything like an x to the third? No. So I bring it down. X squared, do I have any like terms? I do. Negative 5x squared and positive x squared. What do those combine to give me? Negative 4x squared. Okay, then I've got a negative 5x. Do I have anything it combines with? Negative 6x. That combines to give me negative 11x. Positive 30, it has nothing to combine with. So right here, this would be the general form. You give me the function f of x equals x to the third minus 4x squared minus 11x plus 30. So this or what's written in red there are both acceptable answers. All right? And you're going to have to know how to go between the two forms. So I think it's just good practice. Okay, here's the next thing we're going to look at. This is something that I've hinted at because you need to know a little bit of it with the rational functions. But here it is. We're going to explore it a lot more in depth now with polynomials. It says if x minus r all raised to the nth power is a factor of a polynomial f, and x minus r to the n plus first is not a factor of f, then r is called a zero of multiplicity. Okay, wow, that's really wordy. I didn't get that far into it before. It's called a zero of multiplicity m of f. So basically, this is what we're looking at. If I had a function and say that the factored form was x plus 2 squared times x minus 1 to the third times 2x minus 3. Okay? And I ask you to find the x-intercepts. Since these factors are raised to a power, they have a different multiplicity, is what it's called. It means that that x-intercept is happening multiple times. And so the way we show that is a little different. So first, let's just go ahead and find what our x-intercepts are here. So how do we find the x-intercepts? We plug in 0, 4, y, so this would become 0. Right, so instead of saying f of x, I would say 0 equals all these things. Okay? And from there, we're just going to solve it just like we would any other thing that was factored. These three things are multiplied together to give me 0. So that means either the first set of parentheses has to equal 0, the middle one is 0, or the last one is 0. So my x-intercepts are at -2, 1, and at 3/2. Is everybody good to this point? This shouldn't be anything new yet. This is where we're fixing to add the new thing. Okay? So if I ask you for the x-intercepts, this would be your answer. -2, 1, and 3/2. And then I'm going to also ask you for their multiplicity, which is how many times that intercept occurs. So, how many times does the x-intercept -2 occur? It occurs twice because it's raised to the second power, right? And think about what second power really means. That means it's x plus 2 times x plus 2, right? So, I mean, you can literally see it's happening twice. You don't have to write that out or anything, but just make sure that you're connecting all this together. So, the multiplicity of -2 is 2. Now, what's the multiplicity of 1? How many times did this x-intercept occur? 3 times. 3 times. And then how many times did this x-intercept occur? Once. Very good. So it has a multiplicity of 1. And so right now, after we've identified the multiplicity, we're fixing to see what role that plays in the graph of our polynomial function. But let's do one more example where we talk about graphs and their multiplicity. Sorry, look at a factored form of a polynomial and talk about its multiplicity. Okay, so here I've got a polynomial function. I'm on the bottom of 179, example 5. Polynomial function, f of x equals 5 times x minus 2 times x plus 3 squared times x minus 1/2 to the 4th. Okay? And it tells me to find the zeros or find the roots or find the x-intercepts, right? They're all the same thing. I can't say that enough times. So I said each one of these factors equal to 0. So first, what happens when I set 5 equal to 0? That can never happen, right? So that means that doesn't give me any intercepts. Right, so then I look at the set of parentheses. That would give me x minus 2. I don't know why I drew parentheses. What if it was 0? Then I would have an x-intercept at 2. Okay? And what is the multiplicity at 2? It is 1. Very good. There is no exponent. So we'd say the multiplicity is 1. Okay? Look at your next set of parentheses. X plus 3, where it equals 0. Very good. And what's the multiplicity there? 2. Absolutely. And then lastly, you get x minus 1/2 equals 0. So that's going to be at 1/2. And what's the multiplicity there? 4. Very good. So we all good at identifying intercepts and their multiplicity. Now we're going to talk about what that means graphically. Okay. So right here, we're pretending that we have an x-intercept at some number r. Okay? R can be any number. It's just where the intercept occurs. And let's say that the multiplicity, let's say that the multiplicity of r is an even number. So that means the multiplicity is 0, 2, 4, 6, 8, 10, right? any of those things, anything that's even, that means that our graph is only going to touch the x-axis at R. All right, so let's think about an example here. So if I had a parabola that just touched an x-intercept, say here at 2, that means the parabola would come up to it and it would bounce off. All right, we had a problem like that on our last test, if you remember when we graphed it, that the x-intercept only happened once. Because why did the x-intercept only happen once? Because I had plus or minus the square root of 0, right? So I added 0, I subtracted 0. But really, that one x-intercept happens 2 times. Because if you add 0 and you subtract 0, you get the same thing. So it's happening twice. So we would say that this intercept has a multiplicity of 2. It has an even multiplicity. So anytime you have an x-intercept with an even multiplicity, it's going to bounce off. Now, the flip side of that, if we have some x-intercept R that has an odd multiplicity, then the graph is going to cross the x-axis. So, your most basic ones of those, you've graphed lines for a long time. Lines are just polynomials to the first degree. Okay? So what would be your x-intercepts here? Well, you'd plug in 0 for y, and you would say there's an x-intercept at -1. So when I graph this, how many times did that -1 occur? It occurred 1 time. Okay? The graph of this would look something like this, where it's a line going straight through it. So when I have a multiplicity of 1, your graph's going to go through it and just go straight through it. Now here's a little different one. Say that I had the polynomial function f of x equals x to the third. Right? You've graphed this. This has been one of our parent functions. What would be the x-intercepts here? We'd plug in 0 for y, and then we would cube root both sides. So what's the cube root of 0? It is 0. So your x-intercept is at 0, and that's the only one I've got. How many times does that x-intercept occur? 3 times. It's a third degree. Okay? So now this time I have a multiplicity of 3. And what happened to the graph when the multiplicity was 3 at 0? Does anybody remember what the graph of x to the third does? No, you're thinking about square root of x. Don't look it up. Don't look it up. That's fine. The x cubed was the snake graph. Do you remember that? So look, it still crosses your x-axis here, but it snakes through it instead of going straight through it. So if the multiplicity is 1, it's going to go straight through. If the multiplicity is 3, it's going to snake through it. All right? And that's also the case, so let me write this as a note. If the multiplicity is 1, it goes straight through. If the multiplicity is 3, 5, 7, 9, or so on, right? Anything else besides 1 that's odd, then your graph is going to snake through. I know that my writing's not the best. I'm not a great note giver. But is that clear enough? You can make sense of that. Any questions about this? Okay, here is a new concept here. It's called a turning point. All right. We talked about these a little bit before, and we called them local maxima and local minima. where the graph changes from increasing to decreasing or from decreasing to increasing. This is called a turning point. All right. Now your graph, say that you have a polynomial, and its degree is degree 5. Then the most or the maximum is the word I'm going to use. The maximum turning points that can occur in your graph is 4. It's always one less, that's what this is saying here. It's always one less than the degree. Now, x to the 5th can have less than 4, but it cannot have more than 4. That's the maximum number of turning points that can exist. So let's just do some examples here very quickly. Say that I were to give you f of x equals x squared. Okay? That's a parabola. That's one of your parent functions. So the graph there would look like this. How many turning points does that graph have? 1. And that's the most it could have. Okay? Now you've got another graph that was a parent function, x to the 3rd. And we just talked about just a second ago, if I were to graph it, it is a snake. So how many turning points does this have? No. None. None. Does it ever change from increasing to decreasing? It's always increasing the entire time. So this has no turning points, even though it's degree 3. It could have up to 2, but it doesn't. We're going to look at some uglier x to the 3rd ones. I call them uglier. They're more fun to me because they've got a lot of character to them. Hey, you like that word? But you can have an x to the 3rd that looks something like this. Right, that's a lot uglier looking at the equation. But say, I'm just doing a rough, I don't know what this is really going to do. I know it's going to have, well, just don't even talk. The graph could look something like this for an x to the 3rd, where I've got the 2 turning points. You see them? So they're not always, x to the 3rds do not always have 0 turning points. They're allowed to have up to 2. But if I turned again, it could not be x to the 3rd. All right? So now we're going to take that information and we're going to go a little bit further. Okay, this part is pretty quick. You're probably not going to be tested on this a lot or ask a bunch of questions about this part. But here we're asked to determine which of these graphs could be a polynomial function. Now, polynomial functions are what we call smooth and continuous. So continuous means there are no asymptotes, there are no holes, there are no gaps, right? Jumps from one to another. That's what it means to be continuous. What it means to be smooth is, the way that I think about it, if I were to, say I'm pretending like I'm building train tracks. If I were to take a train and make it go 50 miles an hour, and I can't, well, let's just say 30 miles an hour. It doesn't matter. This is just my thoughts. Say the train's going 30 miles an hour on that track. If the train is going to derail because it can't make it, then it's not smooth, right? So just looking up here at these examples, looking at C, you see this really sharp turn? That's called a cusp, okay? That's called a cusp in the graph. So this graph would not be smooth because of that cusp, all right? So when I'm asked, which of these could be a polynomial? Could A be a polynomial? It could not because there is a gap. Could B be a polynomial? It could be. It could be. Could C be a polynomial? No, we just talked about it. It has what's called a cusp, so it's not smooth. And what about D? D also could be a polynomial. All right? So make sure you see the difference between a cusp, because, I see here this is really sharp, but you see how they're rounded off, kind of like parabolas are. That's why we talk about there's a big difference between the absolute value V and a parabola U, because the absolute value is not continuous, or it's not smooth because it has that sharp bend in it. So the last one also could be a polynomial graph. Okay, one more tool that we're going to add to our toolbox is what's called end behavior. It's basically, what does the graph do as you get closer to positive infinity and negative infinity on the x-axis? How is my graph ending? So there are really 4 different possibilities. Okay? The graphs both ends could go up, right? That's the first thing. Both of the ends could go up. Another one, they both could go down. Right? That's the only 2 ways that they agree. They're either both up or both down. Or the end behaviors could disagree. One could be in one direction, one could be in the other. All right? Or it could be flipped exactly the opposite. Still one in one direction, one in the other. These are the only 4 possible end behaviors. So, the first thing I'm going to tell you about is their degree. So think about the things that we know how to graph already. We know how to graph degree 2 polynomials, which is called a quadratic. And we know what a degree 3 looks like in general, right? Because of its parent function that we graph. So when I look at A, which one does A remind you of? Degree 2. What does B remind you of? Degree 2 that's been reflected, right? What does C remind you of? Degree 3. And D? Degree 3 that's been reflected, right? So the degree plays a role. If, can I say it again? If the end behavior agrees, which means I've got my X and Y axis here. If the end behavior is both up or the end behavior is both down, then we know that it is of even degree. Think about your degree 2, right? It's of even degree. And they always agree on the ends. So if I have a degree 2, degree 4, degree 6, 8, 10, whatever polynomial, they're going to agree. Now, vice versa, if my end behaviors disagree, so I have one up, one down, or the exact opposite way, one up and one down, these are going to be of odd degree, right? And we're talking about the polynomial, right? The polynomial is of even degree or of odd degree. We're not talking multiplicity. Make sure you know the difference, because they both deal with exponents. All right, so I've identified right off the bat, these are even degree, these are odd degree. Now, how can I know if my parabola opens up or opens down? If it was a parabola, how did we know? A quadratic. How did you know if it opened up or opened down? Very good. Leading coefficient, right? The number in front of your highest degree term. If it was positive, it opened up. If it was negative, it opened down. The same is true even if it's a 4th degree, 6th degree, 8th degree. The same is true. So if your leading coefficient is positive, it opens up. The next case here would be the leading coefficient being negative. Absolutely. So this one is leading coefficient negative. All right. And now then the next two are a little trickier to remember. So there's a couple of ways you can do it. You can think, which way does an x to the third parent function go? It normally snakes like this, right? Which would be this third form here. Right? The way that I normally think about it is, as my x's increase, I normally want my y's to increase as well. I mean, that's just the way they generally work. And if they're not, it's because of a reflection, because I made the leading coefficient negative. So this one here is when my leading coefficient is positive. This one is when my leading coefficient is negative of a third degree or a fifth degree, seventh degree, any odd degree polynomial. So this would be leading coefficient positive. And this would be leading coefficient negative. Now, we're given a polynomial function. It tells me it's x to the fourth plus 5x to the third plus 5x squared minus 5x minus 6. I need to take all of this information and figure out which one of these could be the graph of my polynomial. So the first thing I'm looking at is the degree. The degree of this polynomial is 4. So since the degree is even, I know the end behaviors have to agree. All right, they all do agree here. So the next thing I'm going to look at is the leading coefficient. What is my leading coefficient? It's 1, which is positive. So if my leading coefficient is positive, the graph's got to open up. So it cannot be D. I've eliminated that. The next thing I'm going to look at is the maximum number of turning points. Since this is a degree 4 polynomial, how many turning points is it allowed to have? 3 or less. Yes. So the most turning points possible are 3. So A, how many turning points are there? There are 3, so it's still good. In B, how many turning points? 1, 2, 3. It's still good. C, how many turning points? 1, 2, 3, 4, 5. It's got too many turning points. So C is not correct. Okay? And now, the next step we're going to go to is we're going to figure out the y-intercept, which is really easy, right? How do we find out what the y-intercept is? We plug in 0 for x. So if I plug in 0 here, 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 and here, I'm left with negative 6. So it has to cross the y-axis at a negative spot. Look, right here it crosses on the positive y-axis. Here it's on the negative, so it can't be A. The only one it could be is B.